Hello, and welcome to CS 500 Design and Analysis of Algorithms with focus on algorithm analysis. Last time we talked about the various ways of analyzing algorithms beyond the classical paradigm of worst case running time, namely, for example, average case running time or amortized running time or expected running time. And also we considered different cost measures beyond running time, such as memory use or communication volume. And today we're going to have a brief recap of CS 300 Introduction to Algorithms to illustrate the general approach that we're then going to extend in the main part of this course. Let me start sharing the screen. So we're going to recall part from CS 300 Introduction to Algorithms, which is a mandatory requirement prerequisite for this course, but for your benefit, we're going to recall that. Namely, first, we're going to recall what I call the virtues of computer science, the characteristics that distinguish computer science from electrical engineering, namely with a focus on the foundations. Then we're going to talk about the power of abstraction, which allows us to develop highly efficient algorithms without getting lost into minor detail, or what Donald Knuth called the root of all evil is premature optimization. We're going to review classes of asymptotic growth like polynomial and exponential. And I'm going to remind you why asymptotic efficiency is arguably more important for the general picture and also more easy to analyze than absolute running times, such as measuring times in seconds or minutes. And finally, we're going to look at the prototype example of these virtues, namely the classical sorting problem, with emphasis on why it's important to specify the problem first before starting to solve it. And finally, after having solved it, prove the algorithm that we found to be optimal, and thus allows us to stop searching for more efficient algorithms. So that's our plan for today. So the virtues of computer science. What makes computer science different from electrical engineering, although both evolve around digital computing technology. The difference is that computer science is a science and electrical engineering is engineering. And here you see as a symbolic picture the 7 classical virtues of humanism, and a picture of Ada Lovelace, the arguably first programmer in history. And these virtues that distinguish computer science from electrical engineering start with first specify the problem that we want to solve unambiguously. That can be formal, but can also be informal, as long as it leaves no ambiguity as to which problem we want to specify. And I'm going to illustrate that at the end of chapter 1 with a sorting problem. Then the next virtue is designing algorithms as opposed to writing program or writing a heuristic. This is different, and I'd like you to not confuse algorithms with programs and heuristics. And 3 characteristics of algorithm design is first to specify the primitives that we are going to, that we are using in the design of the algorithm. For example, integer incrementing could be such a primitive, but also sorting could be a primitive, or sorting could be considered as a compound operation and not a primitive. That depends really on the layer of abstraction, as we're going to discuss in the next slide. So which primitives are permitted when we use, for example, exponentiation, which leaves the realm of integers, and for example, natural exponent function may result in even transcendental numbers, or may we only use integer operations, only bit operations. Next characteristic is what is the semantics of these operational primitives. For example, integer operation, when incrementing 255, will the result be 256, or will the result be 0? Both semantics occur in various programming languages, and therefore it's important to specify the semantics, because different semantics result in different program operations, obviously. And finally, specify what is the cost assigned to each of these primitives. For example, integer multiplication primitives, do we only count the number of integer multiplications, which means assigning cost 1 to each integer multiplication? Or do we want to look more closely and arguably more realistically and assign cost n log n to each integer multiplication, which is a more accurate reflection of the actual bit cost? And same for sorting. Do we count the number of sorting operations, or do we assign costs like n log n to each sorting operation? So these are the some three characteristics that distinguish algorithm design from programming, coding, if you like, and from heuristics. Namely, heuristic is definitely useful, but may not be accompanied with our next step, namely algorithm analysis. Algorithm analysis means that we make sure, formally or informally, that the algorithm we have designed in the second step is actually correct, both in terms of producing the result according to the specification and according to the efficiency analysis that we have conducted here in this step, n log n, for example. And finally, proving the algorithm that we have designed and analyzed to be optimal, so that we can stop looking for a more efficient algorithm, or if it turns out the algorithm is not optimal, then start over again in this kind of meta loop on the second step, algorithm design. And we'll discuss that in chapter 6 of the present course, complexity theory with a tour to P versus NP problem. So these are the virtues of computer science. And now we like to emphasize the benefit of the power of abstraction. So what is power of abstraction? It means that we ignore many aspects of the computer that we're using in order to be able to focus on the important parts. And which parts are important may actually differ from situation to situation. And you probably have been ignoring many parts of the computer all the time. So the purpose of this slide is to make you aware of all you have been ignoring and thus you have been harnessing the power of abstraction, maybe unknowingly. Namely, if you recall, computers are based on transistors, and a transistor, you see a picture of the historically first transistor, is a complex quantum mechanical system. To really understand the behavior, the electrical behavior of the transistor, requires to understand semiconductors, electron band theory, and basically boils down to quantum mechanics, which fortunately nowadays computer users don't need to first take a course on quantum mechanics, because they can abstract from that physical device transistor to an integrated transistor, and furthermore to such a symbol as a control switch. It's the first level of abstraction. Next level is combining transistors into integrated circuit on such a board, again, making it more abstract and more tractable by using these symbolic circuit diagrams, and furthermore integrating them into one integrated circuit. That's the next layer. Next layer of abstraction is combining these integrated circuits into a board, a circuit board, or even further into one single central processing unit, and again ignoring how all these single IC integrated circuits were combined into just the single operation or single lever of abstraction CPU. And then CPU accompanied with memory and control units on a motherboard, which is all subsumed into computer hardware, and again generally ignored by means of the basic input operating system, which operates on that hardware and allows us to kind of hide all the hardware details, so that now we proceed to the software. Software uses device drivers, which is the next layer, then operating system, then object library, and then high-level programming. And all this subsumed in such a computer. And one benefit of abstraction is that we can replace parts of this layer of abstraction. For example, we can replace this desktop computer with a laptop computer, or we can replace one operating system with another one and still use the same high-level programming language. So these are many benefits to the power of abstraction, and these are all ignored, and allows us to write high-level programmings in algorithm design and analysis without needing to know quantum mechanics, for example. So that being said, let's now move on to asymptotic efficiency. We're going to analyze algorithms as we did in CS300 with respect to their asymptotic efficiency. And one reason has been put forth by Donald Knuth, who said that perimeter optimization is the root of all evil. Let's not focus on absolute running time, on seconds or milliseconds or hours, but instead on asymptotic growth. And in order to illustrate that, consider the following table. Here you see a table, and what the rows indicate different input sizes, input size 10, 100, 1,000, 10,000, 100,000. And the columns indicate different running times of hypothetical computer. So here, for example, this is a hypothetical computer which makes one operation per second. This is a very slow one, which only makes every 10-second operation. No such computer actually exists, to the best of my knowledge, but let's suppose so. This is a millisecond clock computer. This is a microsecond clock computer, which makes like 1 million operations per second, like historically the Apple IIe. And this is a gigahertz computer, nowadays common clock frequencies. Also in these columns are indicated algorithms with different asymptotic performance. So these are the absolute timings, and then there are the asymptotic running times, like this is a very slow computer is running an efficient algorithm, a logarithmic time algorithm. And the fastest computer, the gigahertz computer, is running an exponential time algorithm. And in between, so our megahertz computer is running a cubic time algorithm, our millisecond computer is running a quadratic time algorithm, our second computer is running a n log n time algorithm, and so on. So what you see here is really the trade-off between absolute running time and asymptotic running time. Now, which one is more important? What do you think? Well, the answer is in the table. For small inputs, it's indeed absolute running time that dominates. For example, here, the gigahertz computer is fast, but it's already on par with a megahertz computer run a more efficient algorithm. And as the input size increases from 10 to 100 to 1000 and so on, then really the benefit of asymptotic efficiency becomes striking and much more important than absolute running time. And this is another reason why we focus on asymptotic running time. And the third reason is analysis. Asymptotic performance allows to simplify and actually to treat algorithm analysis, which may become intractable when really trying to count every single operation. Of course, as you recall, right, so this is the focus on algorithm analysis as opposed to empirical program evaluation with a stopwatch, for example, to measure seconds or minutes. Of course, asymptotic performance is more important and more simple, right? So here you see different classes of asymptotic growth. And one important part of asymptotic analysis is that we ignore many parts. So for example, when we talk about a quadratic time algorithm, that means we ignore linear time contributions, and we also ignore constant factors in front of the asymptotic growth. So here you see different classes from constant running time via logarithmic, sublinear square root, linear, quasi-linear, quadratic, cubic, polynomial in general, superpolynomial, exponential, double exponential, and tetration. And you see how these grow asymptotically. Here, for example, the factorial. So that's about classes of asymptotic growth. And now let's proceed to an example of algorithm design and analysis, namely the classical sorting problem. So let's recall what is sorting about. Of course, everybody knows what sorting is about, except if you look more carefully and more closely, there are actually different conceptions, subtly different. So let's make it explicit and thus illustrate the benefit of problem specification before starting problem analysis. So in the sorting problem, we're given an input, and the input is given in an array whose values come from some set X. Imagine that set X could, for example, be the set of integers or the set of strings over some alphabet. And also, in this case, we consider the array size as part of the input. As I said, other conceptions are also possible and reasonable. That's why it's so important to clarify which specification we're considering in sorting. And one popular specification of the sorting problem is that the output should be the set in sorted order, right? But that's already ambiguous, right? Do we want the output to be in non-decreasing order? Do we want it to be stable? Or do we want to output the actual permutation that that converts the input array into such a sorted array? These are different conceptions, and here we follow the convention that the output should be not the sorted set, but the permutation that turns that set into a sorted set, so that we can the user can apply it later whenever the user desires. So here's you see an example depiction of a sorting algorithm, namely an algorithm that can only sort 3 elements. So here this algorithm cannot sort any array, but only array of size 3, which is maybe not very interesting, but illustrative, because you recall we agreed that the array size here is part of the input. So our algorithm should in general be able to sort any array, but this one can only sort arrays of size 3. And we use that to illustrate the other aspect of virtues of computer science, namely proof of optimality. So here we talked about specification, and now you recall from CS300, we've designed and analyzed various algorithms for sorting, such as bubble sort, quadratic time, or insertion sort, running time n log n, merge sort, running time n log n. Quick sort was subtle, right? Quick sort naively had quadratic running time. Worst case, only when we would apply this sophisticated method of pivot choice using the linear time median algorithm, then quicksort would boil down to running time n log n. And but then we proceeded to prove that n log n is actually optimal, which is illustration of this virtue, the last virtue of computer science. So let's recall, how did we prove that quicksort and insertion sort and merge sort are optimal? We proved that any comparison-based sorting algorithm requires at least n log n comparison. So that's n log n is required for every comparison-based sorting algorithm. And we proved that mathematically, right? So mathematics is a huge part and factor in algorithm design and analysis. And to remind you, so first we defined what is a decision tree. A decision tree for sorting n elements is a binary tree whose internal nodes are labeled with tests, comparisons of specific array elements, namely array element I with array element J. So here, for example, it means compare a first array element to the third array element. And this means compare the second array element to the third array element. And the leaves, so these are internal nodes, and the leaf nodes here are labeled with permutations of the input array of 3 elements that turn the input array into a sorted output according to our specification. That means that after applying the array, then the input data will be non-decreasing, right? We cannot require it to be increasing because some elements might actually be repeated. So that's also important to make sure in the specification. We cannot require the output to be increasing, but we require it to be non-decreasing. And you can verify that these permutations of 3 elements really have that property once we proceed to from the root through to the down to the leaves. According to the semantics of these tests, every input array of 3 elements proceeds in some way through this tree until ending up in a leaf, and that leaf is indeed labeled with a permutation that produces a sorted output of the input array. And then we proved some mathematical properties of these decision trees. Namely, we proved that any binary tree with n factorial leaves has depth at least n log n asymptotically. This was just a basic application of Stirling's formula, and observe that this decision tree is a binary tree, and we know that the decision tree has n factorial many leaves because every input array, every input permutation ends up in a different leaf. And the connection between decision trees and sorting algorithms, as you know them, naive sorting algorithms, that every comparison-based sorting algorithm of running time T of n can be unrolled into a decision tree of sorting n elements in this sense of depth at most T of n. So the running time of the comparison-based sorting algorithm gives rise to a decision tree with small depth. And on the other hand, item C says that any decision tree with many leaves must have at least a certain depth. And finally, the observation in between that any permutation ends up in the unique different leaf and therefore any decision tree must have at least n factorial leaves. And then putting all together, these three items, that was our proof that any comparison-based sorting algorithm must have depth at least n log n. So that was our illustration of the virtues of computer science, and particularly some virtues that you may not be familiar with from everyday life, namely importance of specification and proof of optimality. And these virtues will guide us through this course, CS500, Design and Analysis of Algorithms. So that already concludes our first chapter, an introduction recap. So we talked about the virtues of computer science that distinguish computer science from electrical engineering. We talked about the benefits of abstraction, high-level approaches, such as high-level algorithm design using algorithmic primitives instead of solving quantum mechanical Schrödinger equations for transistors. They talked about classes of asymptotic growth and the importance of asymptotic efficiency. And finally, we talked about two of the maybe lesser known virtues, namely specification and proof of optimality, at the example of the classical sorting problem. So that's already all for today. And next time we're going to start with chapter 2 on examples for amortized analysis. So I'll stop the slides. And as usual, I'm going to stay online for a few more minutes to answer your questions in the chat. So for now, already thanks for your attention and see you next time.